find the equation in the graphic?
Well, what is lattice energy? Like, what is it? All right, let's go back to the example again. It's the cation and the anion coming together to form a salt. Right. All the other ones, all the other reactions are just there to get us to the ions. Okay. So how do I know magnesium is 2+? Well, magnesium is always 2+. Right. How do I know chloride is -1? Well, I know chloride is always -1. It's a halogen, right? And then they form in a 2-to-1 ratio. So with the lattice reaction, you're always just writing out the reaction for the ions coming together. Okay, so now when we look at this, all of these reactions have to add up to the formation reaction due to Hess's law. If I look at this, okay, let's look at what cancels. So magnesium gas cancels right there on both sides of the arrow. Let's see, what else cancels? Does chlorine gas cancel? Yeah, magnesium +1 cancels. The magnesium 2+ cancels as well. Alright, now we have to do, let's see, what about the chlorine? Yeah, the Cl atom gas, okay, cancels. Now, the one thing, what about so I look at my formation reaction and I say, okay, do I have any chloride ion in there? And I don't. So I got to figure out a way to cancel out the chloride ions. How can I do that? I got to multiply this reaction by 2. So that now I've got a 2 in here and a 2 there, and I also have 2 times the electron affinity. Okay, and that lets me cancel out the chlorides. But now we got an issue, right? Because now we got to deal with the fact that there's now 2 chlorine gases, but there's only 1 up here. So that means now I need to multiply that one by 2 as well. So multiplying 2 times 1/2, this just gets me to now be a 1. This is now 2, and this is now times 2 here. So now I've got my 2 chlorines gaseous atoms, they're now canceling. I've got 1 Cl2 molecule here, which is okay because I got 1 Cl2 molecule down here. And I still have my magnesium solid up here, which also comes down here. So let me box in our final. So we want to keep this, and we want to keep that. These 2 add up to these 2 down here. And of course we want to keep our magnesium chloride solid, which is right there. And everything else got canceled out. So, instant replay. Let me walk backwards. Rewind. Okay. Watch a football play like backwards and see the wide receiver. Anyway, okay. So we wrote out all of our steps. It gave us all of them except for it gave us all the steps except for the actual lattice energy equation. We wrote the lattice energy equation based on our knowledge that the cation and the anion are coming together to form a salt. That's the lattice process. Okay, and so we got that red reaction here due to that. And then we said, well, how do we add up all of these to make this formation reaction at the bottom come true? All right, and by seeing that I needed to cancel out the chloride ions, which are not in the formation reaction, I had to multiply this electron affinity 1 reaction, I had to multiply that by 2, but then that forced me to also multiply this other chlorine reaction up here by 2, so that everything cancels out. And then now the problem is easy from here, because now we just have to, again, add up all these numbers to the formation reaction. All right, so let's do that. So it's going to be the same process as what we have up here. So what we know is that we have 147.1 kilojoules plus 2 times 122 kilojoules, the 2 here coming from the fact that we had to multiply that reaction by 2. For the third one, we have 738. Fourth reaction is 1450. Fifth reaction is 2 times negative 349. And then we have the lattice energy. And all of that is going to be equal to the heat of formation, which is negative 641 kilojoules. Now it should look just like this first one we did, all right, mathematically at least. All right, it does have one more step in it, you know, because with magnesium you got to ionize it twice to make it 2+, whereas with sodium we only had to ionize it once, you know, to make it +1. So that means the lattice energy is going to equal to negative 641 minus this whole thing on this side. Just to expedite this a bit, I'm just going to write the numbers in. So that would come out to be something like negative 2,522 kilojoules. Questions? Do we use these calculations for covalent bonding? No. This is only the bonding model for ionic compounds. All right, so this is just calculating energy changes for when salts form. Okay. Let's also think about what are the numbers telling us. Does it make sense that lattice energy for sodium chloride is less negative than the lattice energy for magnesium chloride? Does that make sense? Why does it make sense? Right, for sodium, yeah, something's going on here, right? So for sodium, you know, we've got sodium +1 and chlorine -1 coming together, right? But for magnesium 2+ and chloride minus, and then you get another chloride minus, right? There's more opposite charges combining for this salt. And so as a result, the greater the charges, okay, the more exothermic the lattice energy. Conversely, the greater the lattice energy in general, the higher the melting points of the salts. Right, so magnesium chloride will have a higher melting point than sodium chloride will. Right, so this does affect the actual physical world. We're not just talking about like numbers and throwing all this theory at you, you know. So the physical properties of the solids are affected by this.
So why did you have to write the red question?
So that all of the steps add up to the bottom equation.
Oh, yeah, equation, okay.
Yeah, so this is really an application of Hess's law. Hess's law is saying that if you have all the steps of a process, they will add up to the overall reaction. And going back to chapter 6, that wonderful chapter that drove people crazy. So the lattice energy is the missing brick in the wall for this whole thing. All right. Anything else? So again, this is for ionic bonding. We're not really to a covalent model yet. Okay, so now, what if they ask you, oh, what are all the steps to this process? Write every step involved in the formation of LiF. I'll leave the example for magnesium up here. This is not asking you to calculate anything, it's just asking you to write the steps. So for lithium, where do we start? Well, let's look at the magnesium chloride example. Instead of magnesium now we have lithium. Okay, instead of chlorine we have fluoride, right? Fluorine. So what do you think has to happen with lithium? Has to go from solid to gas, right? So there's going to be a sort of enthalpy of vaporization for that, right? Actually, silly me, that's not vaporization. What is it? Going from solid to gas, what is that? Sublimation, right? So delta H subbed. All right, and then what else has to happen to sodium? Just like what do we need a well, what had to happen with magnesium? It had to be ionized, right? So, how do we write the ionization for sodium? Gas. So the ionization energies that we talked about last time, those are the energies required to ionize 1 mole of a gaseous free atom, right? So it's in the gas phase. Okay, so that's, do we have to do a second ionization for lithium or no? We don't, right? Because it's an alkali metal, they always form just +1 ions. What about the fluorine? What has to happen with fluorine? Before we ionize it though, what do we have to do? Because it's a diatomic element, right? What has to happen to it? Yeah, right, we have to make it into an atom. Okay, and to make it to 1 mole of fluorine gas, fluorine atoms rather, okay, we've got to have a, this is actually called the bond energy. All right, and then what has to happen to the fluorine? That has to be ionized. But are we ionizing it or are we giving it an electron? So it's the non-metal, it's going to be gaining the electrons, right? So it goes from F to F minus. So this is the electron affinity for fluorine. And then what's left? Let's go ahead and write the bottom reaction. Okay, Okay, if I'm going to form 1 mole of lithium fluoride, alright, what are my elements? Alright, standard form of lithium, lithium solid, plus 1/2 of the F2. So again, going back to formation reactions, it's the enthalpy associated with forming 1 mole of a substance from its standard elements. And then what's the last thing? Yeah, lattice energy. Okay, what's the lattice energy for this? Or what is the reaction? Li plus, okay. And F minus, and that goes to lithium fluoride. So do all of these add up to the bottom equation? Alright, let's check. Lithium gas, that's out. Fluorine gas, that's out. Lithium plus 1 is out. These F minuses are also canceled out. So what do we have left? This guy's left. That guy's left. And this is left. And they add up to our formation reaction. So this problem wasn't giving you any numbers, it just said, okay, set up the problem. That's what that problem said. These are kind of fun, believe it or not, after a while. Like once you get the hang of it, they're kind of fun. Yeah?
Would you ask us to put in like the diagram order, or like just down and then going up?
Nah, I could, I guess, but to be honest, that kind of bores me. I'll be honest. I kind of, I mean, I'm more interested. Can you just set up the series of equations and do the Born-Haber calculation? You know, you don't have to write the diagram. Good question, though. I was just like, thank you. Any questions whatsoever? So if you can, I kind of tried to scaffold this a bit. First, I just showed you all the reactions, showed you a calculation. That was the sodium chloride example. Then I showed you the magnesium chloride example, where it didn't give you the lattice energy equation. It expected you to come up with it and then do the calculations. And then this next example, we didn't give you any of the steps, and you had to come up with all the steps. Okay. Here's one last example that we can do in problem solving later. But what if it gives you all these energies, and now you got to write out all the steps for calcium oxide, and then do the calculation, right? You know, so that would be the last thing. So we'll work on that in problem solving. But for the sake of moving on, I'm ready to move on. Okay, just some factors affecting lattice energy, just in general. I mentioned the ion charge, like +2 for magnesium versus +1 for sodium. So, two main factors affect lattice energy of salts. One is the size of the ions, and the other one is the magnitude of the charge. So if you look at lithium chloride, okay, the lattice energy for lithium chloride is -834. And as you go down from lithium to sodium to potassium to cesium, what happens to the atomic radius as you go down the first column of the periodic table? It gets bigger, right? It's because you have more of a shielding or screening of the outer electrons by the inner core electrons, right? So more of that screening plays out, you know, quantum mechanically and it plays out in the lattice energies of the salts, and it also plays out by extension to the melting points of the salts. Right? So we see that change in physical property based on, you know, the idea of atomic size. Right? So it's always really cool if you can see how the quantum world plays out in the physical world. You know, it's kind of cool. So the reason why lithium chloride then would have a higher melting point or a more exothermic lattice energy, the reason for that is because lithium is a smaller ion relative to these others. So as the ions get bigger, the lattice energy gets less exothermic and the melting points will decrease. Okay, so so why is it more exothermic here? It goes back to this whole deal. If the R between the nuclei of the atoms is smaller, then E becomes more negative, but it's a greater negative number. Right? So Li plus, Cl minus, plus minus, this whole thing's going to give me a negative result. But as the distance R between the nuclei is smaller, the atoms get smaller, this becomes a bigger number. But it's negative, so it becomes more negative, more exothermic. Right, so that's what that's telling us. So the smaller the ions, the greater the lattice energy. That's the trend. Smaller the ions, smaller the radius, more exothermic lattice energy. Okay, on the other hand, what if you have the magnitude of the charge that changes? Check out sodium fluoride. Okay, sodium fluoride and calcium oxide, they both have approximately the same distance between their nuclei. So now this isn't a matter of atomic size or ion size. This is a matter of the extent of the charges. +1, -1, +2, -2. These charges attract even more than these two. And so the lattice energy is quite a bit larger, right, for calcium oxide. Does that make sense? So there's two factors. Ion size, magnitude of the charge. Right? Those two things affect lattice energy. All right. Here's a real quick learning check we do. Rank the following in order of increasing melting point. How would I do melting point? What's melting point? How is that affected by lattice energy? Yeah, higher lattice energy, and when I say higher, I mean more negative, more exothermic. They're higher than melting point. Right. So let's try this. Alright, so calcium oxide. Oops, not calcium hydroxide, calcium oxide. And those are the charges, right? Calcium oxide. What's happening also to the oxidation numbers, right? But KBr, +1, -1. You've got KCl. Also +1, -1, and then you have strontium oxide. It's also +2, -2. So just based on the charge, how do you think we could pair these up? And I'm going to say that you could say, well, KBr and KCl are definitely going to have a lower lattice energy. Okay, it's order of increasing melting point, right? They'll have a lower lattice energy, and they will also have a lower melting point versus those two. Right, so those two will pair up, and they'll be lower. So at this point, we got them separated now by charge. What about the atomic or ion size? So which of these two, they're both potassium, bromine and chlorine, which one has the smaller radius? And chlorine is the smaller radius. So which one of these two will have a higher melting point? And the chlorine. So we can say now that KBr will have a lower melting point than KCl. Okay, what about calcium and strontium? They're both with oxide ions, so now we're looking at calcium versus strontium. Which one's smaller? Yeah, calcium is smaller. So now it's going to be strontium oxide, and then calcium oxide will have the highest melting point due to the smaller radius of the calcium layer. So it's +1, -1. +2 -2, but then you could say that calcium has, or calcium 2+ has a smaller radius. Cl- has a smaller radius. Just to reason it out. Just to be more clear, versus SR2+ down here, right? Versus Br-. Okay.
And smaller radius means higher melting point?
Right, smaller radius means higher melting point, because what happens is when you have a smaller radius, the opposite charges can get closer together. Okay, and so when the opposite charges get closer together, that's Coulomb's law, even stronger than before, and more potential energy is released out. You get more lattice energy released out into the surroundings, and you have a higher melting point. Any more questions? All right, I'm moving on from lattice energy. We'll do a few more problems in problem solving. I think once you do those and you get the hang of it, it'll be a lot. As you probably have experienced in here already, once you do it, it'll sink in better and you'll be more comfortable with it. Okay. I want to introduce, not so much introduce, but reintroduce to you a topic from Chem 107. Okay, so this should appear more familiar. So how many of you remember electronegativity from Chem 107? Electronegativity. And do you remember what electronegativity was? What they told you, at least?
The energy to pull away the electrons from
Right, not so much the energy, but just the propensity or likelihood of electrons to go to an atom when it's bonded to other atoms. Okay, so electronegativity, I just call it EM. Okay, it's an atom's attraction to shared electrons when bonded to other atoms. You might remember that there was a chart with a bunch of numbers on it, and fluorine was the most electronegative element, and the lowest was francium. Francium does not want electrons, okay? And that makes sense because it's a huge atom, it's the largest atom, it's got all this screening going on, and any more electrons trying to pile into that atom just aren't going to be held very tightly. So francium doesn't want electrons, but fluorine, on the other hand, loves electrons. These numbers have no units to them, and they're just made up. They're literally just made up, okay? It's a system for comparing polarities, what it is, ultimately. All right, so you have electronegativity. That's the propensity of an atom to attract shared electrons to it. But the atoms in that case have to be bonded to other atoms. What I don't want you to confuse is, don't confuse it with electron affinity, which we talked about in Chapter 8. Chapter 8 introduces electron affinity, and that's the energy that's released or consumed by a free atom in the